So hello and welcome friends to our channel Intro Mech, where we discuss about basic mechanical engineering concepts. So guys, you all know about the limits, fits and tolerances which we have to use widely when we design any kind of part or mechanism. So in those fits we have a clearance fit, transition fit, and then comes the interference fit. Now in case of interference fit, there are some parameters those are required to be considered while designing, and it is required that we should calculate those values so that we can design properly. So let's see what are these parameters and how we can calculate them. So let's first see what is interference feed. Now we all know that in case of interference feed, our shaft is always greater than the hole size. And again, depending on the interference, there are different types like force feed, tight feed and shrink feed. Now in case of force feed, we have to forcefully press the one part into another part, and that requires very high amount of force. Now here comes the requirement of the calculation part, because let's say if you want to press a bearing into the bearing housing, now if there is a force fit, you should know how much force it is required, and if you want to do some kind of automation, then you have to select a, let's say, a pneumatic cylinder. So how will you decide the size of that pneumatic cylinder? Because if you don't know how much force is required, then how you can design that pneumatic cylinder? So here comes the need of force calculation, that how much force is required to have a interference fit. So then we have a tight fit, then it's a little bit less tighter than what we call as a force fit. And then we have a shrink fit, which is called as permanent type of fit, because in this case either one of the part is heated, and after cooling it gets shrinked and we get a permanent type of fit. So it is widely used on the gears, on the shaft, mounting of train wheels, etc. So what are the applications? Examples, we can see the bearing bush assembly, then dowel pin. Sometimes the dowel pins are pressed. We press the dowel pins inside the assembly. Now depending on the hole size and which type of fit we are giving, the force will vary. If the dowels are very small, we can just insert them with the help of hammer or by mere hand also. So depending on the application, we should select the feed, and then how much force is generated, that we have to check, right? So let's take an example. Now here is the typical example we can see. Now this is the shaft. Now this is a hollow shaft, and then we have a hole, or which is also called as a hub. Now you can see the shaft, and at this edge you can see there is an interference. That means this shaft OD is always greater than the ID of this hub, and we have to apply a force so that we can get an engagement length of, let's say, 10 mm inside this part. So this is our requirement. Now how we can decide, or how we can calculate that how much force and torque and all other parameters are required. Now before going into the calculation, let's clear some of the fundamentals. Now here hub is nothing but a hole, and what is the inner diameter? So that is 20, which is a basic size of this hole, let's say. Then the hub hole inner diameter minimum size. Now we are going with the hole basis system. So in case of hole basis system, the minimum size is same as the basic size. So that's how the minimum size of hole will be same as 20 mm. Then we have the hole maximum diameter. So what will be the maximum size of this hole? So that will be 20.004 mm. That is nothing but the tolerance is like 4 microns, we can say. Then what we have is hub inner diameter upper deviation. Now what is upper deviation? Upper deviation is nothing but the difference between your basic size and the maximum size. So here we can see the maximum size is this one and our basic size is this one, so that's why the upper deviation is this one. And similarly the lower deviation is the difference between minimum size and the basic size, as both are same, that's why the lower deviation is 0. Same Now let's consider our shaft. Now our shaft's OD basic size will be same as the ID of the hole basic size, so that's why the shaft outer diameter basic size is same. Then we have shaft outer diameter minimum size. So our minimum size is 20.005 mm and the maximum size is 20.009. Now here you can clearly observe that the maximum size of the hole, let's say, is 20.004, and what is the minimum size of the shaft, that is 20.005. That means even if the hole is at maximum size and the shaft is a minimum size, the shaft is still larger than the hole, and that's how we get a interference fit, right? Then we have the outer diameter maximum size, which is nothing but 20.009. so again this value is larger. So similarly for shaft also we will get the upper deviation and the lower deviation. So these are the values which are required when we do the calculation, and that's why we have done this basic terminology. Now let's check out some online tool with which we can calculate the interference between these parts. Just go on the internet, type AMES wave, just click on that. Here you will get a lot of other solutions, but we are interested in interference, so go to the limits, fits and tolerances. Here you will find interference brace and shrink fit calculator. Just click on that, the calculator will open. Now here you can see the calculator, right? And this is the basic terminology which we have already explained. So these are the input parameters. Now see what are the input parameters. The torque to be transmitted, let's say we are transmitting some torque also. Then what is the axial force, if we have to put it. Then coefficient of friction between the parts, so depending on the material we should give it. Operating temperature, rotational speed, if we want to give, we can provide. Then the engagement length, as we saw the engagement length in our case was 10 mm, so that value we have to put. This is the engagement length, right? We have to brace that up to 10 mm. Then the hub parameters, as we discussed, the hub outer diameter, the maximum diameter, you can see the outer one was 40 mm. You can go back and check the dimensions. Then the hub inner diameter, which we were discussing, 20 mm. The upper deviation as we calculated, and the lower deviation, right? So that is 0 because this is a hole based system, and upper deviation is 4 microns. Then we have stress concentration factor, modulus of electricity depending on the material. Now this is for steel, yield strength, Poisson's ratio, coefficient of thermal expansion, density. Now all these parameters are material dependent, so you should be careful while giving input of these values, because those will affect the results a lot. So you should know the materials. Now shaft parameters, shaft outer diameter is same as inner diameter of hole, which is 20 mm, which we have seen, that is the basic size. Then what we have is inner diameter, the shaft is hollow, so you can check. Then the outer diameter, upper deviation, what we have is 9 and micron, 5 micron. Then again stress concentration factors and same material properties we have to input for the shaft also. So it in this application we have considered both the shaft and the hole are of same material, but in many time sometimes it happens that the bush is of different material, so that's how we should take care of these values. Then the shrink fit design, the clearance obtained after the shrinking, these value you can give. Then the temperature, then the design factors, so factor against sliding, then again yielding of the hub and yielding of the shaft, you can give some safety factor, and just click on the calculate. It will take some time and then will produce the results. Now let's check out the results over here. You can get the dimensional parameters which we have already calculated. Maximum shaft outer diameter, so then minimum shaft outer diameter, what is the max hub inner diameter, and minimum hub inner diameter. So these are nothing but the values which we already had, and from these values we actually give the input of the deviations, right? So these values are very important. And then we have the limit values for diametral interference, maximum and minimum, that also you can calculate. And interference parameter, the minimum required interference pressure and force of safety. Now here you can see it is in red because we required a 2 factor of safety, but it is lesser than that, that's why it is showing in the red. So that is how you can you can know that this is less safety. Then we have assembly parameters, the temperature of shaft assembly, then for assembly if cooling shaft, and other parameters are given. Now we are interested, and then the stresses and all those things. We can see the green value indicates that the shaft is these values are safe. Now we are interested in force. So here comes the force, the assembly force range to press fit. So the range is maximum is 3 kilonewton and minimum is 0.3 kilonewton. So this is how now we have got the value that in order to press this shaft inside that hole we require a maximum of 3 kilonewton of force. Now from this value you can select either your pneumatic cylinder or any other application which will produce this much amount of force and can press inside the hole. Now let's change some value, and we can again check how it is changing. So let's change the hub inner diameter to, let's say, 30. So shaft outer will get changed to 30, and let's just calculate again. Now the values will get changed. You can see now the values have changed again. The safety for sliding has again gone down, and the force you can see it has now reduced to 1.8 kilonewton. Earlier it was 3 kilonewton, so that has got reduced. So this is how you can check that how the other parameters are affecting and which parameter is dependent on which parameter, and you can check the stresses generated in the hub, stresses generated in the shaft, and you can check the factor of safety which you are getting. So this is how you can find out the force required in case of interference feed, and this is very important parameter whenever you come across some major design considerations, and you have to find out the interference feed. And by mere hand calculations it is not easy, and it is not it is kind of time consuming. So you can use this online tool, but the thing is you have to be very careful about putting the input values properly, because if you put the wrong input values, definitely the output will affect. So this is it guys for our today's session. I hope you got some new knowledge, and if you have any doubts, please do write into the comment section and we can discuss over there. Until then, keep intro making. Thank you for your patient listening. Thank you.